Hello everyone, welcome to this lecture. In the previous lecture, we studied frequency domain representation of continuous periodic signals. This was done using the Fourier series expansion of the signal. In this lecture, we are going to talk about frequency domain representation of continuous aperiodic signals. First, we will talk about Fourier transform, then we will look at inverse Fourier transform, and then we will look at an example of the Fourier transform of an aperiodic signal. And then at the end we will look at the relationship between the Fourier transform of an aperiodic signal and the Fourier series expansion of a corresponding periodic signal. So, this is briefly the outline of the course lecture today. So, today our topic is frequency domain representation of continuous aperiodic signals. So, let us first of all look at what are aperiodic signals, right. So, the aperiodic signals, they do not repeat, right. For example, if I apply an impact force on a structure, okay, then that force signal is not periodic. So, we can represent the impact force in this manner using this graph. Force is in the form of a small pulse, right. So, this is an aperiodic signal, and then it is going to cause the acceleration of the structure, and if we measure the acceleration, then that acceleration may look something like this. Like this. So, acceleration again decays with time. So, this acceleration signal is also not periodic, because this acceleration signal, it decays and then after that it does not repeat. So, now how to find Fourier transform of such signals? Certainly we cannot use Fourier series expansion here, because Fourier series expansion involves representing the signal through a sum of harmonic signals at discrete frequencies, and because discrete frequencies are basically involved, therefore the sum would always lead to a periodic signal, which cannot represent this aperiodic signal, okay. So, then what can be done to represent this such signal in the frequency domain? Let us see the basic mathematical technique or the strategy that is used to obtain the Fourier transform of these signals. So, for the purpose of discussion, let us take a rectangular pulse signal, which is an aperiodic signal, okay, and this signal is in the form of a rectangular pulse like this, okay, and so we have this x as t, right. So, this is a rectangular pulse signal, it is an aperiodic signal, okay. So, it is an aperiodic signal. So, now we can look upon this aperiodic signal as a periodic signal whose time period is infinity, right. So, which means that this signal can be assumed to be a periodic signal, and which repeats after an infinite length of time, and since infinite time is something which can never be achieved, and hence effectively the signal does not repeat, right. But mathematically it offers us a way to basically treat the Fourier transform or to obtain the Fourier transform of this signal. To understand this point further, let us consider a corresponding periodic signal, okay. So, let me show here periodic signal like this. This is the original signal we had, and now we consider basically repetition of the copies of this signal. So, which basically gives us the a periodic signal. So, if I repeat this signal like this on both sides, right. So what we see is that now this signal is repeating after a time t, right, after a time t this is repeating, and of course this is t by 2, this is minus t by 2. So therefore this is the original aperiodic signal of time period t, right, and then this is repeating after every time t. So this we can call as the corresponding periodic signal with period t, okay. And now if we assume that this time period t, if it is increased, okay, then what will happen? The copies of this aperiodic signal, the separation between them will increase. So if I sketch one of such copies, one of such signals, then I have this the periodic signal like this here, and then if I increase t, then the next copy will be farther away like this, and then I have on this side also another copy, right. So you can see. So in this manner, if the t is increased and if it is, and if a limit is taken where t tends to infinity, then this corresponding periodic signal basically will start representing the aperiodic signal we have. So therefore to obtain the Fourier transform of the aperiodic signal, we can find the limit of the Fourier series representation of the corresponding periodic signal such that the time period of that signal tends to infinity. So that limit can be found out, and that should nothing but be the Fourier transform of the aperiodic signal. So this strategy we will use to find the Fourier transform of the aperiodic signal, okay. So let us go to the next page. So let us formally write down what was the strategy that is being used. Strategy being used is that find the limit of Fourier series expansion of a corresponding periodic signal with period t when t tends to infinity, okay. So this is basically the strategy which we will use to find a Fourier transform. So let us now look at the Fourier transform, which is nothing but the frequency domain representation of the continuous aperiodic signal. So we start from the Fourier series expansion, right. So we start from the Fourier series expansion of the corresponding periodic signal, okay, and that we know that the coefficients CR, the complex series coefficients, they are given by CR 1 by t integration of x of t into to the power minus I r omega naught t dt, and the limits are from 0 to t, right. So we can take the limits also alternatively from minus t by 2 to t by 2. So now when if you look at the omega naught, which is the fundamental frequency, that is 2 pi upon t, that is nothing but the fundamental frequency of the signal. Okay. And if you look at the gap, or if you look at the frequency resolution, which is nothing but the gap between the two consecutive frequency components, then that also is actually equal to omega naught, right, because in the Fourier series expansion the components exist at omega naught, 2 omega naught, 3 omega naught and so on. So, the difference or the frequency difference between the two consecutive components is nothing but omega naught. So, this is nothing but the frequency resolution or frequency gap. Okay. So, now when T becomes very high, right, when T is increased, then what is going to happen? The frequency gap will reduce, okay, the delta omega will reduce, and when T tends to infinity, then this gap will become infinitesimally small. Okay. So, go to the next page. So, let us write down the expression for CR, which can be now written as CR is equal to, we can write in place of T 1 by T, we can write down delta omega upon 2 pi integration from T by 2 to minus T by 2 x of T e to the power minus I r delta omega T and dt, right. Now, when T tends to infinity, okay, then the frequency gap delta omega, it becomes infinitesimally small, and therefore, this can be then represented by d omega. The discrete frequency component r delta omega, right, r delta omega is the frequency of the rth frequency component, and that now component no longer remains discrete, but now the components exist continuously, frequency components exist continuously, and therefore, this discrete frequency component can be represented by a continuous frequency variable omega, because now it can occupy any value. And also the strength of the rth frequency component CR, that also becomes infinitesimally small, and since delta omega also becomes infinitesimally small, we then try to determine the limit of the quantity CR upon delta omega upon 2 pi, right. So, we try to find limit of this particular term instead of finding the limit of CR alone, right, because that is going to anyway becomes infinitesimally small. So, now with this we can write the limit as limit T tending to infinity of quantity CR upon delta omega upon 2 pi, right, is equal to limit T tending to infinity integration of T by 2 to minus T by 2 x of T e to the power minus I r delta omega T dt, right. Therefore, on the right hand side we can write the integral as integral with limits from infinity to minus infinity x of T e to the power minus I r delta omega becomes omega dt. Okay. So, the integral basically becomes a function of omega, right, it is a continuous function of omega, and the left hand side therefore is denoted by x of omega, the limit of CR upon delta omega upon 2 pi. This limit when T tends to infinity is symbolically represented by x of omega, because the right hand side has turned out to be an integral, okay, in which omega is a variable. Okay. T of course is an independent variable, and that is the variable of integration, but omega is a parameter in the integral, and therefore the left hand side is basically a function of omega, right. So, therefore, this is nothing but the frequency domain representation of the periodic signal. Okay, and it is in the form of an integral. Okay, so that is why it is also called as Fourier integral. Or also called as Fourier transform. and this allows us to go or to convert a time domain signal into a frequency domain signal, and hence it is also called as forward Fourier transform. We should note that this now is a continuous basically spectrum. So, f x of omega is a continuous function, and therefore, it is a continuous spectrum. Against the line spectrum we got for continuous periodic signals. So, Fourier series expansion gives us a line spectrum, and the Fourier transform gives us a continuous spectrum. And also we should note that the units of x of omega, if x of t, let us suppose, has units of, let us say, displacement, if it is a displacement signal, then let us say the units are meters, right. Then the units of x of omega would be meters per unit hertz. Okay. So, we should understand that x of omega does not give us the amplitude of discrete frequency components directly. We can obtain the discrete frequency components from x of omega by multiplying the x of omega by the frequency resolution of the discrete frequency spectrum. So, let us look at now inverse Fourier transform. So, if we want to reconstruct the signal, right, in the time domain from its frequency domain representation, then what can be done? That can be done through inverse Fourier transform. Okay. So, basically it will allow us reconstruction of the signal x of t from x of omega. Okay. How to do that? So, let us look at the Fourier series expansion. If you look at the Fourier series expansion, right, reconstruction based on that. So, Fourier series or we can also call it inverse Fourier series expansion, right. So, that is nothing but x of t is equal to summation from Cr e to the power I r omega naught t, with r varying from minus infinity to plus infinity. So, this is nothing but the inverse Fourier series expansion, which basically allows us to find out the x of t if the frequency components Cr are there. So, now again we can find the limit of this when t tends to infinity. So, we see that when t tends to infinity, as we said before, r omega naught will basically change to, will become a continuous variable omega, right. And the number of components, because omega becomes continuous, we cannot any longer have discrete sum. The summation therefore has to be replaced by integration, right. So, the summation has to be replaced by integration, okay. And so that is the, I think those points need to be accounted for. So, let us write down this when x of t is equal to, we can rewrite this as sum from r is equal to minus infinity to plus infinity. Now, Cr upon delta omega upon 2 pi into delta omega upon 2 pi into e to the power I r omega naught t, correct. Now, we find a limit when t tends to infinity. So, what is going to happen on the right hand side? In a summation sign we will replace by integration, right, and now the limit of CR upon delta pi delta omega upon 2 pi, this limit would become x of omega, that we have found in the forward Fourier transform, that this particular limit of CR upon delta omega upon 2 pi is nothing but x of omega. And now delta omega basically becomes tends to d omega, right, it becomes, it should be replaced by infinitesimally small quantity d omega, and to the e to the power I r omega naught basically becomes a continuous variable omega, right, and then we have 2 pi here. So therefore we get this, we can write this limit as 1 upon 2 pi integration minus infinity to plus infinity x of omega e to the power I omega t into d omega. So that is nothing but the inverse Fourier transform. Right, which allows us to basically conversion of the signal from the, or transformation of the signal from the frequency domain to the time domain. Let us go to next page. Let us now take an example to find a Fourier transform, right, and let us take the example of the rectangular pulse signal. So let us say this is the rectangular pulse, let us say it spreads over t naught by 2 to minus t naught by 2, and let us say the amplitude is a, right. So let us take this pulse. So this basically rectangular pulse effectively represents some kind of an impact or impulse basically in the time domain, okay. So this rectangular pulse basically gives a idealized representation of a impulse in the time domain. Now if we want to find x of omega, we have to use forward Fourier transform, and the expression for the forward Fourier transform is x of omega is equal to integration of x of t e to the power minus I omega t dt, with t varying from minus infinity to plus infinity. So this is nothing but the relationship for Fourier transform. So now we can substitute a signal here, and because the signal exists only over the limit minus t by t naught by 2 to plus t naught by 2, the limits of integration also can be changed from t naught by 2 to minus t naught by 2, and the signal is simply a, right, into e to the power minus I omega t dt, right. And if we integrate this, basically what we get? We get e to the power minus I omega t upon minus I omega with limits from t naught by 2 to minus t naught by 2. So now if I apply the limits, then what do I get? E to the power minus I omega t naught by 2 minus e to the power minus I omega, this will become plus now, t naught by 2, isn't it? And now we know relationship, right, for sine omega t naught by 2, that relationship is e to the power I omega t naught by 2 minus e to the power minus I omega t naught by 2 upon 2I. So we know this relationship, and therefore if we make a substitution here, what we get? E to the power minus I upon minus I omega, and this quantity is nothing but now minus 2I sine omega t naught by 2, right. Therefore we get E upon omega by 2 sine omega t naught by 2, and we can also write this as a t naught into sine omega t naught by 2 upon omega t naught by 2. So, this is nothing but the expression we get for the Fourier transform of this rectangular pulse signal. Okay, and we notice that now this is no longer a discrete basically series, but it is a continuous spectrum because omega here is continuous. So, it is a continuous spectrum. So, if we sketch the magnitude of the spectrum, then it may look something like this. Similarly, on the it is symmetric with respect to the magnitude axis like this. So, this is nothing but magnitude of x of omega, and this is nothing but the frequency axis omega. And in the same way we can plot the phase of x of omega, there can be a separate plot for that. So, let us see that how the Fourier transform of an aperiodic signal is related to Fourier series expansion of the corresponding continuous periodic signal, right. So, let us quickly sketch what we mean by these two quantities. Already we have discussed that earlier, but let us quickly sketch that. So, this is the aperiodic signal, right, and if we look at the corresponding continuous periodic signal obtained by repeating the copies of the aperiodic signal with after every time t, right, this is t minus t, this is plus t by 2, this is minus t by 2. So, now for this aperiodic signal the we have already seen that the its frequency domain representation is given by x of omega, while for this continuous corresponding continuous periodic signal with period t the frequency components are given by complex Fourier coefficient Cr. Now, the question is there a relationship between x of omega and Cr? Yes, there is a relationship, and the relationship is that the discrete spectrum we get for this corresponding continuous periodic signal, it is a sampled version of the Fourier transform of the aperiodic signal. Okay. So, this Fourier series expansion, it is a sampled version of the Fourier transform. Right. So, if I want to know what is the what is Cr, right, then I can then determine the Cr from x of omega by multiplying the x of omega at the discrete frequency at which the Cr is required by the frequency resolution of the discrete spectrum. Okay. So, therefore, in this manner I can represent the x of omega by a discrete spectrum, but in doing so we need to multiply the values of x of omega at the discrete frequency components by the frequency resolution of the discrete spectrum which I am trying to use. So, in this way today we discussed the frequency domain representation of aperiodic signals, and we learned the concepts of Fourier transform and inverse Fourier transform. So, I think we can now stop here. Thank you.